Okay, let's start again. So, and the idea today is to finish very quickly, to discuss very quickly gauge fields so that we can actually write a proper gauge theory on the lattice. And then I want to discuss very briefly a way to determine the strong coupling constant in QCD using lattice simulations. Okay? So, again, as I said, very briefly, introduction to gauge fields on the lattice. Again, we're going to start from the continuum, and we can start from, let's say, a free field in the continuum. A free fermion field. Okay, so we can write the action as the integral of, let's say, psi x id slash psi x, like this. And then, as you know very well, you can add a sort of color degree of freedom, okay, to the fields, and the action is invariant under global transformations, okay, where psi, which now has got a color index, goes into some lambda r ab psi b, okay? And lambda r typically is going to be some SUM gauge transformation that we can write in the following form, like omega a ta r, like this, okay? Where the ta r are the generators of your gauge, of your symmetry group, and I've added an index capital R just to remind us that matter fields can be in an arbitrary representation of the gauge group. Okay? So typically in QCD we will work with matter fields in the fundamental representation, but this is not necessarily the case. Okay? And when you try to build, for instance, theories beyond the standard model, you may be interested in theories that have matter in a representation which is not the fundamental representation of the color group. Okay? So now, as you know very well, the free action up here is not invariant. Okay? If we make these transformations local. Okay, so if the transformation is depends on the position in space-time. Okay? And you may have seen the solution to this problem. Okay, so if you want to have a theory which is invariant under local transformation, you basically replace the derivative with a covariant derivative. Okay, the problem here is that when you make the parameters dependent on space-time, then the derivative acting on the transformed field is also going to act on the parameter of the transformation. It's going to give you an extra term. Okay, so basically, in order to build a theory which is invariant under local transformation, you replace the standard derivative by a covariant derivative, which is defined in the following way. So we have d mu, and now delta cd. These are indices in color space, plus ig, a mu a. This is my gauge field, TR. This object here has got color indices, and it's upside down. Okay? And now, if you transform a mu under gauge transformations. In the following way. Then you're guaranteed that under local transformations, d mu psi goes into lambda of x, d mu psi of x. Okay, so the covariant derivative transforms in a covariant way, and therefore the theory becomes symmetric. Okay, this is all sort of stuff that you've seen before. Yes. Okay. Now the idea is to see how to translate this kind of theories when space-time is discretized. Okay. So you see, in introducing the covariant derivative, you can really think of the geometric interpretation of a covariant derivative. Okay, and so you can think of the gauge field as an affine connection in color space, right? So the covariant derivative is really the generator of the parallel transport in color space. So as you move in color space, at the same time, you're also rotating the matter field. Yes? Does that sound sort of familiar? Then, because it's precisely this kind of geometrical meaning that is going to inspire the way we define a gauge field on the lattice. Right? So if we're on a lattice, remember we introduced, so we replaced derivatives with finite differences. And so if you look at if you look again at the free action, this contains a term which is of this form. Okay? And here the non-invariance under local transformations is obvious, right? In the sense that psi of x plus a mu transforms into lambda r of x plus a mu, psi of x plus a mu, psi bar of x goes into psi bar of x, lambda r of x dagger, and these two factors do not cancel. Okay? So, in the spirit of what we did in the continuum, where we replaced the simple derivative, which is the generator of translations, with the covariant derivative, which is the generator of sort of the parallel transport in color space, what we need here is that we need to introduce a parallel transport along the links of the lattice. Okay? So this is the generator of an infinitesimal parallel transport. Here we don't have infinitesimal shifts, we've got finite shifts. So what we need is that we need to introduce something which is a parallel transporter along the link of the lattice. Okay? So the way to do that is to introduce, well, precisely the parallel transporter x mu. So this is the parallel transporter which is associated to the link starting at x in direction mu. And this is, if you have a theory in the continuum with an affine connection, then the parallel transporter is just Ig times the integral from x to x plus a mu of dx sigma a sigma a x t a r. Okay? So if you were in the continuum and you had an affine connection A, okay, then the parallel transporter along a line from x to x plus a mu would be defined exactly like that. Okay? And now, what is that? I mean, that's an element of the group. Okay? So, these objects here live in the algebra of the gauge group. The path-ordered integral of the exponential of an element of the algebra is actually an element of the group. Okay? So in order to introduce gauge fields on the lattice, we're going to introduce so-called link variables. Okay, so this ux mu. Now we're going to forget the connection with the continuum description. Okay? We're just going to introduce variables associated to each link, which we call u, which are elements of the group. Okay? These are called link variables. And we're going to define the lattice gauge theory in terms of these link variables. So you see here we've taken a slightly different route. Okay? When we were looking at the scalar field, we said, okay, let's just discretize naively. Okay? We took the continuum action, we replaced derivatives with finite differences, and that was it. But because the gauge fields are so closely related to the sort of, to the geometry of color space, in order to define a gauge theory, it's actually more useful to start from considering the symmetry properties. Okay? And then if you do that, it's very natural to actually associate gauge fields to link variables. Okay? Now, given the transformation properties of the affine connection, you can derive the transformation properties of the link variables. Okay, so under the gauge transformation, you can show that the link variable transforms like this. Hopefully, I've put all the operators in the right order. Yes, and so we can actually use these parallel transporters to define a covariant derivative, which I will denote exactly by the same symbol as the finite differences. Okay, so apologies for the polymorphism of symbols, but otherwise we run out of letters very, very quickly. Okay, so we can define the lattice sort of covariant derivative in the sort of intuitive way. Okay, so we do a parallel transport to x plus a mu, and we subtract psi x, like that. Okay? So you see, in the absence of the gauge field, okay, so if a is 0, all the link variables are equal to 1, and this reduces to the usual finite differences. Okay? When you switch on the gauge field, you get this extra group element that multiplies psi, which is also the reason why we're using just the same symbol. Okay? When there is no gauge field, u is 1, but you can keep the same. You can keep the same definition. And likewise, for the backward derivative, as an exercise, find out how to define the backward derivative. Okay? Now, it's clear that under gauge transformations, what happens to, let's see what happens to the covariant derivative. So u transforms like this. So we get the factor of lambda at x. Okay, then we have psi at x plus a mu. So we get a lambda r of x plus a mu, psi x plus a mu. and then get minus lambda r at x times psi of x, okay? And then these two factors cancel, and so this transforms covariantly, as you would expect, okay? So this is just the sort of natural extension of this instruction to the case where instead of having infinitesimal distances in space-time, you can only move by a finite amount which is dictated by A. Okay? So as an exercise, try to find out an expression for the backward derivative. Okay? You will need, again, a factor of u in the appropriate place in such a way that the backward derivative also transforms covariantly. Okay? So these are our basic variables. Okay? If we want to put gauge fields on the lattice, we're going to define an element of the gauge group, not of the algebra, of the gauge group, for every link in our lattice. Okay? And the physical interpretation is that these are the parallel transporters from one side to the other in color space. So we've got our variables. What do we need next? To define a quantum field theory, we're going to need an action. Okay? So how do we build an action? Well, again, let's look at the continuum action for a second, and let's try to understand what kind of guiding principle we can take from the continuum case, and then we will apply that to the lattice theory. Okay, so in order to build the lattice action, we can start from the continuum theory. Remember, the action in the continuum theory is proportional to the dx g squared, okay, where g mu nu is the field strength tensor, okay? So you can call this g mu a t a. This is an element of the algebra as well, and you can write it as the commutator of two covariant derivatives. Okay, we're not going to get into the details of this. It's not particularly useful. What is important here is that, again, this is basically the only operator that you can write that is Lorentz invariant, gauge invariant, since we want to build the gauge invariant theory, of dimension 4 and parity even. Okay? You could add a parity odd term here, GG tilde, which we're not going to discuss, at least not today. Okay? So again, if you think from a sort of an effective field theory point of view, your action is just the only relevant operator that you can write that is consistent with the symmetries of the system. Okay? You can have higher dimensional operators, of course, but they're irrelevant. Okay? So we're going to do exactly the same for the case of the lattice theory. So we're going to try to build objects from these link variables that are invariant under the sort of hypercubic group that are gauge invariant. Now, here there is a difference, of course, that You see here the choice of G squared is dictated by dimension. I mean, this is the only dimension 4 operator in this game. When you go to the lattice, okay, we've got these link variables. These are elements of the gauge group. These are dimensionless quantity. Okay? So there isn't an obvious way of counting dimensions. So in principle, there is a very wide choice of operators that you can write that are gauge invariant. Okay? So how do you build a gauge invariant operator out of link variables? Well, okay, let's have a new lattice. Suppose I take the product of two gauge links, okay? Because of the transformation properties of each of these variables, the product of, let's say, two of them transforms like lambda r of x, u x mu, u x plus a mu, mu, and then lambda r of x plus 2 a mu. Okay? So if you take any product of link variables, all the matrices that are in between link variables will cancel. Okay? So a product of link variables along a path will transform with a factor of lambda to the left at the beginning of the path and a factor of lambda dagger to the right at the end of the path. Okay? So in particular, if we take a closed circuit, okay, so if I call if I call L the product for a set of links that belong to a closed path of u x mu, okay, then this closed line transforms like, let's say, starting somewhere, starting at x. Let's call this point here x. Then this will transform like that. Okay? And so the trace of L is invariant. Okay? So when you take the trace using the cyclic property of the trace, the two factors of lambda to the left and to the right will cancel. Okay? So again, if our guiding principle is symmetry, we can write a lattice action by taking the trace of any product of links along a closed path on our lattice. Now, and that's a lot of choice, and it's good practice in this case is to go for the simplest choice. And so we're going to take 1 by 1 squares, okay? So starting at x, direction mu, I'm going to call P of x mu nu the product of these 4 links, okay? And, okay. Allow me not to write them explicitly, okay? So it's just the product of these 4. Under a gauge transformation, because it's the product along a closed path, this transforms like lambda r p x mu nu lambda r at x dagger, and so the trace of p is invariant. Okay? And so conventionally, we choose the action, the gauge part of the action, to be the sum over x the sum over all directions mu and nu, counting each of them only once, of the real part of the trace of 1 minus p of x. Okay? The 1 in front is just a convention, okay, in such a way that if the gauge field is 0, so if all links are equal to the identity, then the action vanishes. Okay? And then we put a coupling in front of the action, which unfortunately is called beta. Okay? It's called beta because of the relation to statistical mechanics. Right? Remember that this is a Euclidean theory, so we're going to define a path integral as the integral over e to the minus s of u, okay? And then this really looks like a statistical system of, matrices that are defined on each of the links, and beta looks like the inverse temperature of a statistical system. So it's very unfortunate, but this is the definition that was used by Wilson in its original paper, and it's stuck forever in the community. So beta is both the bare gauge coupling and the symbol that we use for the beta functions. So keep an eye on what we're talking about. So using, using this sort of representation for the gauge links, to connect the gauge links to the gauge potential, you can actually compute the naive sort of continuum limit of this action. And if you set beta over 2n, where n is the number of colors, equal to 1 over g squared, then S of u in the naive continuum limit, where a goes to 0, tends to the continuum action, the function of a. Okay? So we can also think of beta as 2n over g squared. Okay? And sometimes I'll be talking about g squared, sometimes I'll be talking about beta. Typically, whenever you do something which is really close to perturbation theory, you tend to talk about g squared. When people do numerical simulations, they tend to set the value of beta in the action. Okay? So this is our path integral here. So this completely defines our gauge theory. Okay? And as we said before, in the case of the scalar field theory, in the case of the fermionic field theory, this is a definition which is non-perturbative, right? Which goes beyond perturbation theory. You don't need perturbation theory to make sense of this expression. And in particular, as I said a moment ago, you can think of this as a statistical Boltzmann weight, and then you can compute path integrals by Monte Carlo integrations. I mean, we're not going to spend any time discussing the numerical aspects of lattice field theory, but the reason why this is useful in practice is because these kind of integrals can be computed by statistical methods. Okay? So you've got access to all the correlators in the theory by sort of numerical simulations. Okay. Any other comment? Okay, I should specify what this is. Okay, this is an integration measure over the gauge group. It's the R measure. It has got some properties, but again, we don't have time to sort of get into the details of that. There's an important comment here. Because we've gone from the gauge potential, which is an element of the algebra, to these link variables that are elements of the group, all these integrals here are over a compact space. Okay? So while the algebra is non-compact, I mean the fields in the algebra go from minus infinity to plus infinity, the group is a compact manifold, okay? Which makes life simpler in the sense that, for instance, you don't have to worry about fixing the gauge. Okay? You have to fix the gauge if you want to do a perturbative expansion, so if you go back to the gauge potentials, but if you want to do, for instance, numerical simulations, there is no problem fixing the gauge because the volume of a gauge orbit is a finite number. Okay? So with this, we have all the ingredients to define QCD, so the theory of strong interactions, non-perturbatively. Okay? So I'm going to write down the action for QCD and then discuss the parameters, and then we'll move to a specific application, which is the determination of the strong coupling constant. Okay? So what is QCD? Well, QCD is a gauge theory. So we have a gauge field, and the degrees of freedom associated to the gauge field we call gluons. This is an SU3 gauge field. And then we've got matter fields that we call quarks, and these are fermions in the fundamental representation. Okay. So given the field content and the symmetries, we can write down the action. Okay. So we will have an action. We will have link variables that are associated to the gauge field. We will have fermionic variables that describe quarks. And then we will have a gauge action, which is just the Wilson action. But by the way, you can improve in the sense that we discussed 2 days ago. You can improve the Wilson action by adding other path, by choosing other closed path of bigger size. Okay? Again, we're not going to get into that, but you can add other contours to the action, the trace of closed contours, and that is a way of reducing the lattice artifacts. But we're not going to discuss that. We're going to stick to the plaquette action. So get beta times sum over x, the real part of the trace of 1 minus px mu nu. And then for every fermion species, we're going to have some discretization of the Dirac operator, as we discussed yesterday. Okay? Or we could even take something which is just a matrix in flavor space. Okay? So, depending on the physics that you're interested in, you may want to include just up and down in the action, up and down and strange in charm. And then if you were in the seminar yesterday, you saw that charm quark becomes tricky on the lattice because it's massive. And so the mass of the charm is close to the cutoff. And so you don't satisfy this constraint anymore. But, okay, it's just at the edge. And then bottom and top are definitely too heavy. Okay? I mean, the top is so heavy that you're not even interested in its non-perturbative dynamics. And the bottom is actually a problem. I mean, the bottom is difficult to include in lattice simulations. There's no problem of principle, but with the current values of the lattice spacing, we struggle to get into the regime where this is satisfied. So then there are solutions, but again, it's not what I want to discuss. So let's keep it simple. We're going to consider the case where we have the gauge field and only two light quarks up and down, and we're going to be in the isospin symmetric limit, so the mass of the up is equal to the mass of the down quark. Okay? So that there are only two parameters in the action, beta and m. Both of them are relevant in the sense that we discussed 2 days ago. Okay. And so both of them need to be tuned in order to describe the correct sort of continuum physics. Okay? So the way this is usually done is using so-called mass-independent schemes, which were introduced originally by Weinberg, where for a given value of G, we tune the bare mass in such a way that we reproduce some physical quantity. Okay, so for instance, the mass of two physical states. Okay? You can measure both of these quantities on the lattice. We're going to discuss this tomorrow. And you can require that this is equal to its experimental value. Okay? So you fix the value of G, you fix the value of M, you measure this quantity on the lattice, and you keep G fixed, and you fine-tune M until you match the experimental value, and then you can compute any other quantity on the lattice, and then that defines A as a function of G. Okay? And that's just AM, which is the quantity that you compute on the lattice divided by the experimental value of the scale. Does that make sense? Remember, we said the bare parameters are functions of the cutoff. Okay? So the way the way they flow is called is your renormalization scheme. So the way we realize the renormalization scheme in this framework is that for every value of G, we fix the value of M by matching some ratio, say, of physical masses, and then we determine the value of A by looking on the lattice to some physical scale, and again, comparing to the experimental value. Okay, so if we do that, we get A as a function of G, which we can invert. We can get G as a function of A, and then we can plug it in here, and so we get M as a function of A as well. Okay, so in this way, we realize a flow, okay, in parameter space. Right? A flow that keeps the physics constant. Does that make sense? Exactly in the sense that we discussed 2 days ago. So that's our theory. And now let me tell you how this is used. I mean, this is now we are really making a jump forward from very basic sort of ideas to something which is extremely contemporary, which is the alpha S determination. And then tomorrow we will spend some time filling the gap, in the sense that tomorrow I'm going to discuss something that has happened in between the sort of very basic work and the more contemporary results. Okay. So let's forget lattice field theory for a second, and let's think about alpha strong. So alpha strong is actually the coupling, the QCD coupling. Okay, so again in QCD, let me call G bar any renormalized coupling in any scheme, the running of the coupling is given by the beta function, okay, as we discussed. And beta function can be computed one way or another. We're going to discuss that. But the important thing is that once you know the beta function, you know, I mean, you can evolve G bar from one scale to any other scale, right? It's a first order differential equation. So all you need is one sort of initial condition, okay? So typically, beta is computed in perturbation theory. I'm going to write this in the following way. Somewhere k from 0, well, in principle to infinity, of b k times g bar to k. Okay. This is a bar power 2k. Okay, so the beta function in perturbation theory starts at order g cubed. Okay. It's not a -3 power, it's g bar cubed. Okay, and then there are corrections that are in powers of that come in powers of g squared. Okay, so if you know an initial condition, you're done. You've determined alpha strong. Okay, and the value, so the beta function will depend on the renormalization scheme, blah blah blah, but basically, once you know the beta function and you have an initial condition, you know alpha strong. And the quantity that is used, that you find in the PDG, for sort of historical reasons, is alpha in the MS bar computed at the Z mass. Okay? MS bar because all the perturbative calculations for phenomenology are in MS bar, so it's a very useful scheme. MZ and Z for again for historical reasons. Okay, so let's start from here, and starting from here, we can rewrite this in the following form. And then we can integrate in between two scales, and we get that the log which I called mu1 and mu2. And this is just the integral between g2 bar and g1 over dx of beta of x. Okay? That's just a trivial integration. And now, you see, if you send one of these two scales to infinity, you get a log divergence. Okay? By the way, the beta function looks like this. Okay, so this is g bar, this is beta of g. So as you go towards the infrared, g bar tends to get larger. As you go to the ultraviolet, g bar goes to 0. Okay, this is called asymptotic freedom. So the log divergence that you see on the left-hand side when you send one of these two scales to infinity is recovered on the right-hand side because beta, because when you send the scale to infinity, the coupling goes to 0. Okay? And beta goes like 1 over x cubed, so this is singular when you integrate at the origin. Okay? Here I should have said g bar 1 is g bar at the scale mu1, and likewise for g2. Okay? So we can manipulate this expression here a little bit and put it in a more friendly form. And again, I won't have time to do every single step of the calculation. So, you know, the important steps is that, as we said, there is a divergence here. We want to understand what the divergence looks like. Okay, so in the beta function, we're going to factor out the 1 over g cubed, in 1 over beta, we want to factor out the 1 over g cubed dependence and see what is left, okay? And if you do a little bit of algebra, you see immediately that this is 1 over b0 x cubed times 1 minus b1 over b0 times x plus higher orders in x. Why did I keep the first two terms? Is because these are the two terms that are divergent when we go to the origin. Okay, so this is divergent, and 1 over x is also divergent. Okay, when you integrate over x, it gives you a log. So the trick is to, in this expression, is to add and subtract the divergent terms in the expansion of 1 over beta. Okay. So I'm going to write this in the following form. So the integral, what is it, from g2 bar to g1 bar of dx over beta of x. We can write in the following form. We can write this as the integral from g2 bar to g1 in dx of 1 over beta minus the divergent part. So that's going to be plus 1 over b0 x cubed minus b1 over b0 x. Okay. And then we are going to add these terms again and perform the integral. Okay? Because here the limits are not 0, I can do the integral. I don't have to worry about the divergence. Okay? And so if you do the integral, you get the following contribution. 1 over 2 b0 g1 bar squared from integrating 1 over x cubed minus 1 over 2 b0 g2 bar squared. And then from integrating this 1 over x, we get b1 over b0 squared. I've got a square here. Log, yeah. Just a second. Let me get all the logs, and then I'll be with you. B0 squared log of G2 bar, like that. Sorry, go ahead. Yes, thank you. Yeah. Okay. So that's just the integral of this term between G2 and G1. And again, check for typos and stuff like that. Now, why is this a sort of useful exercise? Well, we're going to take this expression, we're going to put it in here, and we're going to exponentiate. Okay? And if I do that, I need to find, okay, wait a second. Before I do that, so you see now this integral here, the integrand is no longer divergent. Okay? So I can actually extend this integral to 0, both here and there. So I'm going to take this integral and I'm going to split it into two. Okay? So the integral from G2 bar to G1 bar in dx of all that stuff, I can write as the integral from 0 to G1 bar plus the integral from G2 bar to 0 of dx of all that. Okay? Because now I can extend the integration range down to 0 without any divergence in the integral. Yes? Okay, so now I can take this expression, plug it in there, take the exponential, and what we find is the following. I'm going to write it explicitly. Minus 1 over 2b1 g1 bar squared times b0 g1 bar squared to the power minus b1 over 2b0 squared. This comes from the log times the exponential of minus the integral from 0 to g1 bar of dx times this integrand here, okay? This is equal to the same quantity computed at the scale mu2. Okay, so you replace all the indices, well, not all the indices, but you replace mu1 with mu2, g1 with g2 in this expression, and they're actually identical. Okay? So what this is telling you is that actually this expression here is independent of the value of mu. Okay? Because this calculation was done for arbitrary values of mu1 and mu2, and you find that this combination here is the same for any value of mu1 and mu2. So this combination here is independent of mu. And this is, if you look at dimensions, this has got dimensions of mass, okay? So this is it's an energy scale. It's an energy scale that is called lambda. This is called the Lambda Parameter of Qcd. Write in general like that. Mu, g squared of mu, b0, g bar squared to the minus b1 over 2 b0 squared times the exponential of minus the integral from 0 to g bar in dx of that expression. Okay? Right? So that quantity there is a constant. It's a completely non-perturbative result. It does not rely on knowing the beta function in here to some order in perturbation theory. Okay, all we used was the asymptotic expansion for small g, but this is a completely non-perturbative result. Okay? So you see, knowing the coupling in Qcd is actually equivalent to knowing lambda. Okay? Remember what we said before, the RG equation is a first-order equation for which you need one initial condition. One initial condition means that you need to know g bar at one specific value of mu, okay? And that allows you to compute the lambda parameter. Okay? So the lambda parameter is your initial condition for determining alpha. So this is important because, you see, the determination of alpha strong really is the determination of one scale. You only need one number, you only need one scale in Qcd, and alpha is determined at every energy by the RG. Okay? One single scale gives you your initial condition, and then everything is fixed by the RG. So, yeah, the jargon is that you want to determine alpha ms bar at mz, but really what you need is one scale, is this lambda parameter. So, remember, the lambda parameter is defined from the beta function, okay? This is a b0, and therefore it's scheme dependent. Okay? The beta function is only the first two coefficients of the beta function are scheme independent. So the lambda parameter is scheme dependent, just like alpha is. Okay? There is a nice feature about the lambda parameter, and that is that as you go from one scheme to another, the connection between lambda parameters is a one-loop relation. Okay, so a one-loop calculation gives you the exact relation between lambda parameters. We can leave that as an exercise. It's in the notes. Okay. What else? Yeah, you can also. Okay, and the other thing, of course, is that if you take the limit for mu going to infinity of that expression, you see that as mu goes to infinity, this goes to 0. And so really, you can think of the lambda parameter as the limit when mu goes to 0 of this quantity here. Which simply tells you that the lambda parameter is really an ultraviolet. It's an ultraviolet quantity, right? It's a quantity which really describes the behavior of the coupling at very high energies. And actually, if you take this limit seriously, then this term is subdominant compared to this one. And then lambda simply becomes the scale of the logarithmic running of the coupling. So at very high energy, lambda is just the scale of the logarithmic running. Okay. Okay, good. Any questions? No? Fine. So how do we determine alpha? Not on the lattice, but in general. If you go to the PDG, there is an entire section which is devoted to QCD, and in there's an entire subsection which is devoted to the determination of alpha using all sorts of methods. Okay. Basically, well, first of all, let me remind you what alpha is. Okay, so alpha ms bar at the scale mu is just g ms bar squared divided by 4 pi. It's just a usual definition. And the way alpha is determined is that in general you take some process, some observable p, okay, that you measure at some typical scale q. If it's a tau decay, Q is the mass of the tau. If it's a collision, the typical scale is the energy of the collision. And then you look at the perturbative expansion of whatever observable you have. Okay, you can compute this perturbative expansion in the ms bar. In powers of k. Okay, and then typically this expansion will stop at some order n, which depends on how skillful you are in doing perturbative calculations. So there will be corrections that are of order alpha mu to the n plus 1. And these go under the name of missing higher orders. And then potentially there are power corrections. So, non-perturbative effects that are non-analytical in the coupling. Okay, and this S here is the ratio of mu over Q. And typically, these coefficients have got logs of S. Okay, so in order, if you want to have a sort of a good perturbative expansion, you want to try to keep these coefficients small. You want to avoid large logs. So typically, you want to have mu of the order of q, and then at the same time, you want to have mu large enough. Let me write it like this, okay? Much larger than, say, the mass of the proton, so that the missing higher orders are small. So if you are in this kind of regime and you have a physical process, you take the data and you can fit the value of alpha strong. Okay? That's the way you extract alpha strong from experiment. Now, there are lots and lots of data. I mean, I've been involved myself in doing fits of alpha S, where we take 4,000 data points from a collider experiment with all the experimental error, all the systematics, correlated, uncorrelated. We plug everything into a gigantic fit, and we extract the value of alpha. This is an extremely unpractical way of determining just one scale. Okay? You need to control an awful lot of experimental systematics in this framework to extract what at the end is just one scale. You know, in principle, knowing the mass of the proton, you're done. Okay? You can express if you can relate lambda to the mass of the proton, that's a pure number, you're done. And the mass of the proton is something that we know with extreme precision. So if you can find a way sort of relate this lambda parameter to a low energy scale, you can do a much better job than by fitting data. The challenge, of course, is to be able to relate lambda to some low energy scale. And this is where lattice technology helps. So I'm going to discuss very briefly how you can define a coupling, compute its evolution non-perturbatively, and then match to the MS bar. So if we want to use sort of lattice techniques, we need, first of all, to define a coupling. So it's going to be a coupling defined in a lattice scheme. Okay. We need to be able to evolve alpha p, and then we will need to match to MS bar. Okay. At the end of the day, we do want to determine lambda MS bar. Well, sorry. First determine lambda, and then match to MS bar. Because at the end of the day, I mean, we do want to find the MS bar value of the coupling. So the interesting steps from the lattice point of view are these two. Once you've done these two steps, you are basically done. So the first thing to discuss is how to define a coupling. Well, in order to define a coupling, we're going to use exactly the same sort of strategy that we use for continuum QCD. I mean, for experimental data. Okay? So we're going to define some lattice observable. Okay? Which will be defined, well, let's call the scale directly mu. And then from the lattice observable, we can define a coupling in this scheme P, which is defined, if you like, by the observable, by saying that this is P mu over C1, 1. Okay? So we take an observable that in perturbation theory is proportional to the coupling. Okay? We measure this non-perturbatively by numerical simulations, and then we define a coupling by taking a non-perturbative coupling by taking the non-perturbative measurement and dividing it by the coefficient of the expansion of P. Okay? So this is a non-perturbative quantity that in a perturbative expansion starts like alpha. Yeah? Okay. So, in words, this sounds great. Okay? Let's do it. Where is the problem? Well, the problem is that at some stage, we will want to plug the value into this expression. Okay? And in this expression, here remember there is a beta function. The beta function we only know in perturbation theory. So for this expression to make sense, we want to know not to make sense, but for this expression to give us an accurate value of lambda, we want to use it at high energies, okay? Where the perturbative beta function that you stick in here is a good approximation of the true beta function of the theory, okay? So we want to use this formula, but we want to use it at high energies. By high energies, I mean energies where you are confident that a few orders in perturbation theory give you a small uncertainty. Okay, so let's say, what would you say? What is a scale where you are safe using perturbation theory to a few orders? Let's make a poll. 1 GeV? Probably not. Right? It's the proton mass. Definitely not. 10? Could be, right? We do it, right? We describe processes at 10 GeV in perturbation theory. But how much is the? So, by the way, how much is alpha strong? What's the result that we're aiming for? Do you know? Alpha strong at MZ? Yeah, 0.11. Okay. So 0.11 is a good expansion parameter. Right? At the charm mass, how much is it? At a few GeV? No. At 90 GeV, but MC is a few GeV, right? So 4, 5, whatever it is. Sorry, 1 and a bit. How much is it? It's 0.3. So it's not such a good expansion parameter. Okay. So let's say that a scale where we feel safe is roughly 100 GeV. Okay, is around an MZ. Okay? So, you want to make a lattice measurement of some non-perturbative quantity at a scale which is of the order of 1 GeV. So, you want the lattice spacing to be, remember, so the cutoff introduced by the lattice spacing to be much larger than this scale. This scale is going to be much larger than, say, the mass of the lightest particles. Okay, we said we want it to be of the order of 10 GeV. But if you want to simulate QCD, you want to have pions as well, right? I mean, you don't have a choice. You're simulating the full theory. And you want the pions to sit comfortably in your lattice. You want your lattice to be big enough that the Compton wavelength of the pion is smaller than the volume of your box. Now you see, this is a huge hierarchy. Okay? If you want this to be really of the order of 100 GeV, and if you want this to be even, say, just one order of magnitude bigger than that, this is 100 MeV. So you see, you end up very quickly with L over A, the order of, say, 10 to the third, 10 to the power 4. Okay? Now, these are 4-dimensional lattices. Even 1,000 to the power 4 is a very, very large number. It doesn't fit on a computer, on current computers. Okay? So, in principle, this looks very, very nice, but if you try to do it in practice, you really have a problem with the sort of hierarchy of scales. And so, this problem has a very elegant solution, which is what I really want to talk about, which is something that goes under the name of finite volume renormalization schemes. Okay. So if you're only interested in the running of the couplings, you don't really need to worry about having pions in the system. I mean, having a big enough box so that QCD can happen undisturbed. Okay, you can do something which is much more radical. You can link the renormalization scale to the volume of the box. Right? When you are in this, when you do normally when you do a QCD simulation, you try to take the size of your box as large as possible. You try to go to the thermodynamical limit. You would like to be sort of in infinite volume. Here, we take the opposite approach. We stick to a finite box, and we use the size of the box as the probe, okay, for our renormalization group. So we link the renormalization scale to the size of the box. And then we try to, and then this is okay. We can, we can have 1 over A much larger than 1 over L, which means L over A much larger than 1. Okay, so you don't need to go to 10 to the 4. You can, in these days, we can easily get to L over A of the order of 100. Okay? Basically, we link the size of the box to the renormalization scale. We don't care about the large distance physics. We're only interested in the running of the coupling, and then this is much easier to achieve. Okay, the price that we pay is that the size of these boxes, which is of the order of 1,000 times A, is very small. 100 times A is very small. Okay? So if you want mu to be 1 over L, and if this is 100 GeV, then you end up in a very small physical volume. Okay? This is called the femto. This is called the femto universe. Sometimes it's just a name. It just means that you will be working in a physical volume which is very, very small. Okay? So you cannot use these simulations to compute the properties of the pions, because the pions literally don't fit in the box. You would have huge finite volume effects. Okay? But you can use this kind of setup to compute the, for instance, the running, to define a non-perturbative coupling and to study its running. Okay? So this is exactly what has been done. There are many, many ways of putting the theory in a finite box, and basically, if you're not planning to go to the thermodynamical limit, you need to specify the boundary conditions, and there are many ways of specifying, of choosing boundary conditions. Periodic boundary conditions, which are very useful when you look at the spectrum, because they are sort of they give you translation invariants and everything, are a very bad idea if you want to do if you want to connect to perturbation theory. So perturbation theory in a finite box with periodic boundary condition has got pathologies, in the sense that you end up, because of the zero modes in the box, you end up with an expansion which is non-analytical in alpha. So again, we don't have time to get into the details of that, but you don't want to use periodic boundary conditions. You can use twisted boundary conditions, where at the boundary you apply a twist in color space. But what we're going to discuss today is what is called Schrodinger functional boundary conditions. where you basically impose Dirichlet conditions in one direction. Okay? So, for instance, for the gauge field, AKX at x4 equals 0 is going to be set to some function ck of x, and AKX at x4 equal L is going to be set to some different function C prime. And there is, again, some freedom in choosing these functions C and C prime. We're not going to enter in the details, but typically these functions depend, in the choices that are currently in use, these functions depend on two parameters, eta and nu. Okay? I'm not going to get into the details of the dependence, but typically they depend on two parameters, eta and nu. Okay. So the action of the theory will depend on these two parameters, eta and nu. And so you can actually, it turns out that you can actually define a coupling by taking the expectation value of the derivative of S with respect to eta, computed at eta equals 0. Okay? For a specific choice of these C and C primes, which depends on eta and nu, you can define a non-perturbative coupling by taking the expectation value of the derivative of the action with respect to eta. This turns out to be something that is easy to compute, and therefore it's a useful non-perturbative definition. Okay, and this is related to the coupling following way. This is 12 over pi times GSF. This is called the Schrodinger functional coupling, which is defined at a scale mu squared, where mu is 1 over L. Okay? So, the Schrodinger functional coupling at a scale which is fixed by the volume of the box in physical unit is obtained by computing this quantity. So this is computed numerically. And it defines the coupling through this relation. So this is a non-perturbative coupling that you can compute at a scale mu. Okay? And this is the coupling that we want to run. Okay? So we want to set up a numerical strategy that allows to compute the dependence of this coupling from the scale mu, which is defined by the size of the box. And the way this is done is by introducing something which is called the step scaling function. So, I mean, there are many, many things that we are introducing and defining, so let's try to sort of keep an eye on the logic without getting bogged down by the technical details. Okay? So we define a step scaling function, which we call sigma s of u. Okay? And sigma s is defined as follows. Sigma s of u is the value of the coupling at the scale mu given the value of the coupling at a scale s time mu. Okay? So if you know the value of the coupling at a scale s time mu, and you call it u, sigma s of u is the value of the coupling at a smaller scale. Okay? So this is like the evolution of the coupling from a scale s mu to a scale mu. Yeah? It's like an integrated beta function. And indeed, you can show that the log of S is the integral from u, square root of u, to the square root of sigma u of dx over beta x, like that. Okay? That's an exercise. So this step scaling function just quantifies the running of the beta of the coupling, but instead of doing it in a differential way, like the beta function, it does it over a finite sort of change of scale by a factor s. Yeah? As you do this, you can check, as a sort of consistency check, you can check that the right-hand side is independent of u. Okay, you see this integral has to give you log s for any value of u. Okay, so just as a way to check that you understand the definitions and you know what's going on, you can check that the right-hand side is u independent. So we're almost done. Okay, now we have the definition of the step scaling function. The running is encoded in the step scaling function. Okay, so forget about the beta function. Now we're just going to talk about the step scaling function as a way of describing the running. This is completely non-perturbative because all the input here, so let's do this in the Schrodinger functional scheme, all the input here comes from numerical simulations. Okay, so we're not relying on perturbation theory at any stage there. So what do we do? Well, we do the following. We take a box. Like this, of size L1. We set G and M. Remember the bare parameters in the action. Okay. And we tune M so that the theory is massless, so that the theory is a chiral. Okay. And then we measure the Schrodinger functional coupling. Okay. And this is the Schrodinger functional coupling measured at the scale L1, and this is going to be affected by lattice artifacts that scale with A. Okay. We do a measurement in here, and we get a value. This is the value that we call U. Okay? Then we keep the same bare parameters, and we do the same measurement on a bigger lattice of size S times L1. So we keep exactly the same values of G and M. Okay, so this means that we have the same lattice spacing, because remember that the bare parameters are a function of A, and vice versa, A is a function of the bare parameters. So if we keep the same bare parameters, we have exactly the same lattice spacing. And then we measure again G bar of SF, which now is at the scale 1 over S L1, with, again, artifacts that depend on A. Okay? So this object here is my sigma. I'm going to call it capital sigma, because this is the value that I get from the lattice, including lattice artifacts. Okay, so this is sigma of U, where U is the value that I measured here, okay, with lattice artifacts that are given by A over L1. Okay? So I can measure this for several values of u and several values of a. And then for every value of u, I can take the continuum limit. Okay? So for each value of u, we can define sigma s as the sigma s of u as the limit for a over L goes to 0 of capital sigma of u and a over L. Okay. And so that allows me to compute sigma, the step scaling function, for several values of u. Now, once you have the step scaling function, you can run this coupling. Okay? So you start from the value of the coupling at some hadronic scale. So this is my G bar at some hadronic scale. And then you set a recursion relation where you define gk minus 1 squared to be equal to sigma s of gk bar squared. Okay? You know sigma, so you can set up this recursion relation, and so you can do a few steps of step scaling, and you can, after, let's say, n steps, you have g bar at a scale which is Sn times mu hadronic. Okay? Now you see, this is very powerful, okay? Because at every step you increase the scale by a factor of s. Okay? So if s is 2 and you do 10 steps of step scaling, you have done quite a lot of running. Okay? And remember, in order to determine sigma, you have to go from a lattice of size L to a lattice of size 2L. Okay? So it doesn't require a lattice with 1,000 points. Okay? If you have a lattice with 30 points here and 60 points there, you're doing pretty well. And this is where this method is really powerful, because with a very few steps of step scaling, you can actually run over a wide range of scales. And so you can get, in a completely non-perturbative way, you can get to a regime where you can actually make contact with perturbation theory. Okay? We're not finished yet, but does this make sense? You have to think about it. I mean, it's not. But let's say the basic idea is that you can define a non-perturbative coupling. Knowing the non-perturbative coupling, you can define a step scaling function. The step scaling function is something that you can measure. Okay? And so you get a tool that allows you to run the coupling in a non-perturbative way. Okay? And it's a very effective tool because you only, as I said, you only need a few steps of scaling to get to very high energy. This is not cheap. Okay? To do this correctly, especially to take this limit, requires a lot of numerical effort, but it's doable on current machines. Well, it's not just doable, it has been done on current machines. Okay? So let me get to the end of the story. So we've done the running, okay? And now remember we want to compute the lambda parameter, okay? So we want to compute just one mass. And I'm going to write the lambda parameter in in a way that will become clear in a second. But before we do that, in all this discussion, we never determined the scale in physical units, right? So remember here, what we've done is that we have created an alternative to the running equation. Okay? So you can, if you know the beta function, you can integrate this equation. But the beta function you only know in perturbation theory. So here we found a non-perturbative alternative to this. But we still haven't addressed the problem of the initial condition. Right? The initial condition means that I have to give, a value in GV for one of these quantities. Okay? So let's try to do that. We are going to, and for that we need an experimental number. Okay? So in that sense, you need to use one physical scale to set alpha. So the way to do that is that we're going to rewrite the lambda parameter in the following form. We're going to take some baryon mass. We're going to take the experimental value. Okay? We're going to say that the lambda parameter is the experimental mass multiplied by A mu hadronic divided by A m omega. So this is a quantity that you measure in a lattice simulation, okay, at the initial scale of your step scaling procedure. This is also a quantity that you can measure in a lattice simulation. Then you have mu pt over mu hadronic. This is just s to the n. Okay. This is the scale factor that you get by doing step scaling. And then finally, you have lambda over mu pt. And that is given by the formula that we derived at the very beginning. Okay, so lambda over mu pt is just e to the minus 1 over 2 b0 g bar squared, where this is computed at mu pt times b0 g bar squared the minus b1 over 2 b0 squared times the exponential the minus 0 to g bar of dx. And now in here we can put the perturbative beta function plus 1 over b0 x cubed minus b1 over b0 squared x. Okay. So by step scaling, we get to a sufficiently high scale. So this is non-perturbative. Then we get to a sufficiently high scale where we can extract the lambda parameter using this equation, where here we put a perturbative expansion for the beta function. Okay? And you can show that the difference between having the full beta function and having a perturbative truncation of the beta function goes like g to g squared to the L minus 1, g bar squared to the L minus 1, okay? Where L is the number of loops that enter in your beta function, in the perturbative calculation of the beta function. Okay? So if you determine the lambda parameter at a sufficiently high scale by using this equation and a perturbative expansion of the beta function, the error that you do is of the order of the coupling at this high scale to the power 2 to the L minus 1, where L is the number of loops that you have included in your calculation of the beta function. So if you can run to a sufficiently high scale, then you can compute the lambda parameter with a small uncertainty. Okay? So this is your experimental input. As I said at the very beginning, you need one energy scale to determine alpha strong. It can be the mass of a baryon. It can be, I mean, any mass scale. It doesn't have to be a mass. Any quantity that has dimensions of mass will do. This is something that you compute in a real sort of QCD simulation. Okay, so for this, you need to do a large volume simulation. But that's fine, because this is an hadronic scale. Okay, so you don't have a huge hierarchy of scales when you compute this. The hierarchy of scale is taken care of by the step scaling. So this is done using finite volume techniques. The running from the hadronic scale to a high scale is done using finite volume techniques. And then once you are at the high scale, you can use perturbation theory with confidence. Okay? Now this is becoming, I mean, the reason I wanted to show you this is because this is becoming increasingly important. I mean, as we go into the sort of high precision era of the LHC, right? I mean, the LHC is an hadronic machine. Everything you do requires a precise value of alpha. So, you know, when alpha was known to 5%, you don't care, right? You do this matching pretty much wherever you like, and more or less you're in the right ballpark. Now we're talking of getting a sub-percent precision in alpha, which, by the way, translates into a few percent precision in lambda. Okay. Now, when it gets to that level of precision, you need to take these issues seriously. So you really have to do this matching with perturbation theory at a very high scale. Otherwise, these terms here do hit you badly. Okay? And at the moment, these methods, these finite volume methods, are the ones that give you the most precise determination of alpha strong. You get just below percent precision. There is room for improvement. You see, the problem is that as long as you are at low energies, you have a systematic error, right? You have these missing higher orders in the perturbative expansion. They're very difficult to estimate. Okay, there are all sorts of techniques and, you know, scale variations and whatnot, but it's all at the level of cooking recipes. Here, you get to a regime where you really know that the missing higher orders are going to be small because the energy is very high, right? It's of the order of 100 GeV. And you don't get it for free, right? The price that you pay is that you have to determine the step scaling function with high accuracy. But you have shifted the problem. You shifted the problem from something that gave you some sort of uncontrolled systematic errors to something which you can improve systematically just by increasing the statistics of your lattice simulation. Remember, at the end of the day, this quantity here is obtained from a lattice measurement, right? So this is something that comes out of a numerical simulation. So you switch on a big computer, you make sure you do the right thing, otherwise it's just global warming. But eventually, it's a lot of global warming, right? So one should really think carefully. So, but eventually, you can improve this systematically, right? Just by going higher in statistics. And so So I think this is the very first determination of alpha strong in QCD with all the ingredients. This method has been developed over more than 20 years, and there have been preliminary results. They've always been branded as such. I mean, they never claimed they have got to the end of the story. But basically, a year ago, they got the very first result in full QCD with dynamical fermions and everything that starts to be a proper determination of alpha S using numerical methods. And I think this method is going to stay. I think it's going to take a long time before we find anything better than this. Okay, so let me finish with just a couple of comments again that I think are important. So first of all, alpha ms bar or the lambda parameter are perturbative quantities, right? So in order to compute alpha ms bar, no matter what you do, you have to relate, because QCD is strongly interacting, you have to relate a low energy scale to a scale where you trust perturbation theory. It doesn't matter what you do. I mean, you will always face this problem one way or another. I mean, when you do it from data, it's kind of hidden under the carpet, but you have exactly the same problem. At some stage, you need to compare with perturbation theory, and the energies that you can reach are never sort of the energies where you are safe. The determination of alpha strong from tau is a prime example of that, where you have a beautiful perturbative calculation, a very precise, beautiful calculation. The only problem with that is that the energy there is fixed by the mass of the tau, and the mass of the tau is what it is, and you cannot. So you still struggle with corrections. The other thing is that there is no difference, right, between lattice determinations and determinations from data. At the end of the day, alpha strong is determined by data. Okay? It's not something that you can compute from first principles. Okay? So the lattice is just a technique to do the evolution. But no matter what you do, alpha strong is a renormalized quantity which is determined by an experimental number. If you think in terms of the lambda parameter instead of alpha, you see that really what you need is one scale. Okay? So the coupling is determined by the knowledge of just one scale. And it doesn't matter whether you do it on the lattice or whether you do it from experimental data. I mean, this is the wrong way of classifying the determinations of alpha S. What really matters in the classifications of alpha S is this. Right? Is the scale at which you can match with perturbation theory. Everything else are tools. Okay? You will need an experimental input anyway, so there is no such thing as a lattice determination of alpha S. It's not that from a lattice simulation you get alpha S. What you get from a lattice simulation is the running in a non-perturbative way. And then in all cases, you need a scale, you need an experimental input, and what is really crucial, what should really distinguish the determinations, and at the end of the day, what determines the precision is really how far you can push before you match to perturbation theory. And with that, we should go for lunch.